Okay, for this video, I'm going to start talking about lung dynamics for the assigned study. So basically, to start off, lung dynamics is basically what affects how the airways, how they breathe in and out, how fast you can actually breathe it, right? It's how the motion of the air. So to start off, we kind of like look at three different factors that kind of determine when you put in a certain amount of pressure where those forces are actually going to go. So you'll see there's a characteristics of compliance and elastance of the lungs. So compliance is basically how much it can stretch. There's also resistance and then inertia. So for compliance, it's the stretchability, like how much you can actually stretch the lungs, right? So it's the change in volume that you get per change in pressure. So it's how much volume you're going to get per change in pressure, okay? And then elastance is basically, it's the inverse of that, okay? So the higher the elastance, the more stiff, it's like how stiff the object is. So elastance is just 1 over C. And but what we want to determine is we want to be calculating pressure changes, right? That's what really matters. So we'll rearrange the formula, and what you end up getting is change in pressure equals elastance times the change in volume. Okay, and that's the change in pressure of the compliance. Okay, so that's like the lung, the chest wall when it expands, how much it changes. So then the next one will be resistance. So basically the airway, the faster the air moves, the more resistance you're going to have. And it's all relative to kind of like a function of the resistance of the airways, right? So you can change the size and stuff like that. That will also change resistance. But if we know what the size is and everything, basically change in pressure for the resistance equals the flow rate, so how fast the fluid is flowing, times the airway resistance. Okay, and then the last one is inertia. So basically to get the air moving, it takes some energy, right, to accelerate it. So you could calculate the change in pressure for the inertia, but basically it's neglected anyways because it's quite negligible. They do mention it in the reading, a formula for it. I don't think you got to know it. You can look into it if you want. I'm not going to memorize it. So the change in pressure, the total change in pressure is just the sum of the three, right? So it's a change in pressure of the compliance plus the resistance. And then it's going to be plus the inertia, right? But the inertia is discounted because it's quite negligible. So now looking at compliance, when you actually, there's a thing called surface tension, right, in the lungs. So when you're expanding the lungs, they're going to resist being expanded, and one of the main reasons for that is fluids. When they're on the fluids of the same type want to come together, right? They interact, and they actually have forces that want to bring it together. So if you have your alveoli, right, and there's a fluid around here, this fluid doesn't want to become in contact with air. It could rather be in contact with itself, so that creates forces that pull in. It wants to pull together, and it actually pulls it inwards, okay? So what it does is it pulls the alveolar inwards, and that's what contributes to a lot of the pressure. And so what they can actually do is, if you want to measure the compliance of the lung without any surface tension, what they do is they inject lungs with saline water. And basically, so the lungs will be completely full with water instead of with air. And so then if they graph that, they can actually measure the pressure volume curve and how much it expands. So a normal pressure volume curve, what you'd see when you breathe in, it takes a lot of pressure in the beginning. So this is pressure down here. And this is volume here. Okay. So when you breathe in the beginning, on inspiration, you'll see that it takes a lot of force to even start breaking it. And then it breaks, and you kind of get a curve like that, right? It's a normal kind of pressure volume curve. And then when you're breathing back out, it doesn't drop down right away because the molecules kind of take a while to pull it together. So you kind of see it, it's kind of divided like this, more or less. So this is breathing out, so that's breathing in, okay? Now, if you actually inject the lungs with saline, what you'll see is that the surface tension is more like this. Okay, so this is saline. And so you can see that a large portion of the energy or the pressure being contributed is actually because of the surface tension. So what the body does for that is we actually produce a thing called surfactant, which is it's a lipid. It's a type of lipid that's secreted by the lungs. And what that does is that kind of breaks up this because lipids are hydrophobic. It kind of floats on top, and it breaks off the surface tension. And another thing that's actually quite interesting about it is that it, as it expands, right, it gets spread out. So it contributes less to a reduction in surface tension as the lungs get really big. So if you, when you're looking at surface tension, how much surface tension there is in the object, I think it's called Laplace's law. And Laplace's law basically looks at, so the tension, I think it equals, well, the first way they did the test is they had a balloon, they had a tube with like a soap bubble on the end, and they pushed air through it, and the soap bubble would round like this, right? And so that would be a way, and then they could measure how much pressure you had to put into it to change this balloon, basically, or the bubble. So because this bubble is only a half sphere, basically what they had is the tension equaled, what was it? It was two something over R, or something like that, right? And so basically the surface tension, as R increases, you can see that it reduces, something like that. Okay, but basically as R increases, you can see the surface tension goes down. And in the end, for a full sphere, it ended up being like 4 over pi r squared or something like that to calculate the surface tension. So what that means is that smaller objects actually have a lot higher surface tension than larger ones, right? So if you had 2 interconnected alveoli and one was small and then one was really big, this one would actually want to collapse, right? Because it has higher forces pushing in on it compared to this one that just has little ones pushing in. And what you'd see is you'd see a rush of air into the big one, and it would all end up clumping up into bigger volumes, bigger bubbles, right? But one thing is, because surfactant coats this a lot more, there's way more surfactant in here than in here, which just has a thin layer of it, it actually reduces the amount that those forces kind of interplay with each other. So that's another benefit of surfactant. Moving on to airway resistance. For airway resistance, basically, you can have 2 types of flow that happens. And so because air is free to move around, right, it's always going to be bouncing kind of, and when it bounces loud, so if you have a tube, right, you want the air to all be flowing in that direction, right, all the particles, there's particles everywhere, right? But the problem is, they're not always going to be flowing that way. They could be flowing in either direction, okay? And when they move and hit in other directions, what they're going to do is they're going to end up slowing down the particles in front of it. So that's what's going to be creating the resistance. And so if you have something, it's called laminar flow. So laminar flow. And basically what that is what you'll see is the air flowing on the outside is actually flowing, it's slower than on the inside, okay? And the reason it's slower is because it's going to be moving along the airway, right? So this is causing resistance. And as these bump into each other at different speeds, it'll cause resistance, right? So, but with laminar flow, you'll have all these layers, these nice layers with different speeds, okay? But you end up reaching a point where there's so much back and forth motion as you increase the speed that you end up getting turbulent flow, and when there's turbulence, it's just a huge amount of resistance. The difference is unbelievable, and then that's what's really going to like prevent you from breathing out anymore. You're going to have to apply a lot of force. So there is a formula for calculating the point at which turbulent flow actually happens, or if it's going to happen in the airway. I think it's called the Reynolds number. Reynolds number. And so he actually figured out that it's all proportional. I can't remember the formula, so I'm just going to write it down. It's 4 times the flow rate, okay, over, so the faster the flow rate, the higher the number is going to be, over viscosity times diameter. Okay, so if you have a larger diameter, the lower the number is going to be. And what he figured out is if this number is greater than 2,000, it's going to be turbulent flow. That's basically all you got to know. One thing that I find kind of interesting is that as viscosity increases, and so as to the thickness or the density of the fluid actually increases, it actually reduces the likelihood of having turbulent flow. And the reason for that is as the density increases, you actually have less room for these to move back and forth, and so they'll flow more evenly and be less likely to become turbulent.